seconds or so. Good afternoon, everybody. Welcome to a hot, sunny afternoon of Chem 170 with your host, me, Dr. White. I don't know if you've been out. It's hot out there. I just finished teaching up all morning at College of DuPage. Now, one thing I'm debating, and I'm not sure, I think we'll see how it goes on Tuesday and Thursdays. I finish up about 20 to 1, and I've got to get home, have lunch, and get ready for 2 o'clock. And I finish at 20 to 1. Students ask, I get out of there about a quarter to 1, 10 to 1. I've got to drive home. And so today I made it. In the future, I may move this class start at 10 after 2. But for now, let's see how it goes. All right. Last night, I had a heavy debate with myself, which I've done in the past. I finally came to the conclusion, I think you guys can pull it off, that, and I sent out the following announcement. All right, thumbs up, people. Can you see test number 1 information on your screen? Thank you. All right, so I sent this out this morning, and this Thursday, I will be giving test number 1. I was going to postpone it till Monday. I said no, because you got all today, tomorrow, and even Thursday. And I'll explain why I said that. To study for it. And 3 days here is like a week and a half in normal semester, actually a little more than a week and a half. So let's go through test number 1. Test number 1 has 10 pages, 14 problems. Some of the problems have multiple part. In Chem 170, I never have and never will give multiple choice. It will cover alkanes, alkenes, alkynes, and aromatic compounds. In other words, and also I could have put down here, which I didn't, cycloalkanes. The breakdown, 13 points are general knowledge, like how many bonds to carbon, and nomenclature. The main questions there are, here's the structure, give the IUPAC name, here's the name, draw the structure, and reactions. Excuse me. And if you notice, it adds up to 105. So there's five bonus points on test number 1. Now, at the end of class on Thursday, I will email you a password for the password protected PDF file of test number 1, which you'll be able to download. It's available now for you. You don't have to, from D2L. You'll have until 11 a.m. the next morning, take test number 1 and upload it to D2L as a single file, PDF file. Now, a couple of things. First of all, how do you prepare for test number 1? Do the practice problems, memorize what I told you to do, general reaction, and those tables, and know the IUPAC rules for alkanes, cycloalkanes, alkenes, alkynes, and aromatic compounds. Historically, test number 1, students usually get the highest average, close to 90 for my classes. Some classes, well, not all students study, and I have no control over that. But I hope you all study and do the practice problems, because that will help you with test number 1. I say I'll send out an email with the password. Take up to about an hour. If you need a little extra time, do it to take when you actually take test number 1. And then don't count as part of the hour the time it takes for you to make the PDF file and upload it. Now, if we go to assignments, well, actually, I should have done this. You as a student, go to assignments, you'll see it's already there. And in case you don't know how to use CamScanner to make a PDF file, here it is, other instructions, other ways to make PDF file, just like you do to labs. And this is password protected, and I will send out the email at the end of class on Thursday at roughly 10 to 5 or maybe a little earlier. And you will have until the next morning, 11 a.m., take it, upload it. And the following class next Monday, I will go through all the answers to test number 1, but I will cut it out of the video. I just don't want that floating around the internet for all time. So I don't. All right, the question is, when do you download it? Well, you can do it today. You can wait till tomorrow. You can do it Thursday when you need it. Any day works. It's got a password, so you can't open it up yet. Aren't you glad Dr. White's a power user? Now, listen carefully. And someone asked, and it's a good question. If you don't have a printer, what you can do on a piece of paper or 2 or 3 is just don't write out the questions. Just write out the question number, like question 1A, and your answer. And then you can do all the rest of those, like 5A, 5B, and then you can make a PDF file with your smartphone. If you have a scanner, you can use that, just like you were doing the labs. And if you don't have a printer, just don't have to write the questions. Don't. It just takes a lot of time. You don't need to. Dr. White's good at doing these, so I know the questions I put on my test. And that helps. Nana, does that help you? Thank you. And thank you. All right. So again, remember, test number 1, you'll be taking sometime after Thursday class, and you'll have until Friday, 11 a.m. And that gives you time, if you want to spend more time Thursday studying before the test, do it. And that's the way, and it's worked out well in this class. Okay. Now, a couple of things I realized I had forgotten, bad Dr. White, to talk about on alkenes and alkynes in general. And I'm going to clear that up right now. All right, first one. Let's do this general reaction. Anybody happen to think of alkanes when you drove by a gas station? Before I do this, did you look at a candle and think half the weight of a candle is an alkane? Or do you use Vaseline on yourself or a baby and think that's got alkanes? Remember, organic chemistry is all around you. And if you use the barbecue, the propane is an alkane. Remember, organic chemistry is all around you, and it won't hurt to think about it when you're not in my class. All right, let's get back to this. If I take a double bond, react it with a halogen, you know from we've gone through it, you break the pi bond and each carbon gets a halogen. Now, here's what I wanted to talk about. And look at the following reaction. And let me put it on the board so you can see it. Oh, Jordan asked a very good question. Is the stuff you're learning on Thursday going to be on the test? And the answer is no. And same thing for Wednesday. Today is, yep, it's still Tuesday. Yeah, I put out my garbage. Come on, you should know better. But anyways, I will finish up today everything you have to know for test number 1. But I will continue on to new stuff, and it happens every summer, and actually happens in the fall and winter too. That will be on test number 2, but we're not taking it this Thursday. I always try and end a couple of days early to give you time to study and practice. And that's why my students do good. All right, Jordan, does that help you? You're welcome. Well, let's get back. All right, let's look at the problem which you didn't see. All right, now if I write this molecule and react it with bromine gas, and notice I have the letters excess in brackets. That means you have excess bromine. That means bromine will react with anything it can, because you have all the bromine in the world to react whatever it could. Now, if we look at this molecule right here, oh, look, a double bond. Wait, there are 2 double bonds. And whenever you have a double bonds, 2 of them or more, and they're separated by more than 1 carbon, each one reacts like it's alone. Whenever you have a double bonds, 2 or more in a molecule, and they're separated by 2 or more carbons, they each act like they're alone. So what's the product here? Well, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6. These 2 carbons are like here. You break the pi bond, each one gets a halogen, in this case, bromine. But we also have these 2 carbons, and that's this reaction too. And notice I broke the pi bond, and each carbon gets the halogen. And there are 4 bonds to carbon. And that's the molecule you get. So the key thing here is when you have 2 double bonds in a molecule separated by 2 or more carbons, each one reacts like it's alone. And I want, when there's just 1 carbon, it's a whole new ball game, and I'm not teaching that in this level course. Your turn. What would be the product or products of the following reaction? You're welcome, Jordan. And when you're done, give me a thumbs up. Remember, each one acts like it's alone. Hint. All right, let's do this. What do we have that's different? Remember, look at a molecule. Look, it's not a carbon-carbon single bond or a carbon or hydrogen atom. Ooh, double bond. A second one. We're reacting with chlorine gas, and the general reaction is this. Now, you might ask, why is that there? Because I don't want to balance the equation. I need more than one molar molecule of the halogen because I have not one, but two double bonds. And that just says I have all the halogen in the world to react. Do you break carbon-carbon single bonds? No, there's 6 across. These two carbons are these two. I broke the pi bond, and this becomes this. What's X? Chlorine. But now I have this double bond, and the same thing happens. These two carbons right here are these two carbons, and each one gets a halogen, chlorine, and that's the molecule you get. Now, there's one other thing I want to talk about, but before I move on, it's been a busy day for me. I forgot to mention something else, which I should mention. All right, test's going to be on Thursday. Tomorrow, I will do my, yes, world famous review for test number 1. Now, one of the bad things about D2L, which I need to show you, it's real funky. All right, everybody see lectures on D2L? Thumbs up, people. All right, thanks. Now, if you scroll down, notice up here it has 1 of 33 top. Oh, that's something else. But if you scroll down, at the very bottom, does everybody see the button where it says load more? This thing I hate about D2L. You see this at the very bottom where it says load more? If you click on that, guess what? More things are there. They shouldn't have to make you do that, but they do. And notice I have test number 2, number 1, is both a Word document and PDF. And I'll have to do the same for 2, 3, and 4, because instead of having them handwritten, those are all typed, which will make it easier. I will go through this tomorrow. Also today, we'll finish up aromatic compounds. So tomorrow, I will go through the problem set aromatic compounds. But again, what you have to do, and it's amazing. We go to lectures again, scroll to the bottom, see where it says load more. It's got some hidden. You click on that. Now you'll see the rest of them, and you can see test number 1 review. So remember, when you go into the lecture section, if you want the review, you have to go to the bottom and click on load more. All right, the other thing I didn't talk about, which I should, is the fun part of organic chemistry, but I'm biased about what I'm going to talk about, and that is synthesis. How do you make things? And that's the fun part, but I'm a synthetic organic chemist. That's my training. That's what I did for many decades in the chemical industry. I still do that consulting. Well, let's look at a synthesis problem. All right. Does everybody see that? What is the starting material or materials? Hold on, let me clean something up. Oh, no, it's right. Materials for the following. And you're given a question mark. If it's only one thing here, I may not put the question mark. If it's more than one thing, I'll put two question marks for two things and so on. If you react something with chlorine and make this molecule, well, how do you figure out what you start with? Well, let's look at what's different. Ooh, this carbon has the halogen. The adjacent carbon has the halogen. What are we reacting something with? Chlorine, which is this. Remember, X here can be fluorine, chlorine, bromine, or iodine. And what do you start with? This you should know, a double bond. Now, let's look at this reaction in terms of synthesis. This carbon and next door, the two that have the halogen, are the two in the double bond. Now, going from here to here, are you adding carbons? No. So if I end up with 3 carbons, I better start with 3 carbons. So I end up with 3 carbons, I better start with 3 carbons. Now, what the general reaction tells me is the 2 carbons involved with the halogen, having the halogens, will be the 2 carbons of the double bond, which are these. And then I know there's 4 bonds to carbons, so I can put in my hydrogens. And this is what I call a synthesis problem. Now, as you notice, it's a little more challenging than the regular give the product or products. And because of that, and because at least up to this date, it hasn't changed, I think the Supreme Court of the United States has outlawed cruel and unusual punishment to students. So on test number 1, there will only be one synthesis problem. Test number 1, one synthesis. It can be any of the general reactions I taught you for test number 1, but there'll only be one problem. And why don't you try this one? What would be the product or products? In fact, I'm so used to saying that. What would be the starting material for that reaction? And when you're done, give me a thumbs up. All right, 2 done, 2 to go. Oh, one left. All right, let's do this. Now, how do you figure out what do you react with bromine to make this molecule and look for what's different? Well, we got a ring. That's just carbon, carbon, single bond. Oh, look, what's not carbon, what's not hydrogen? Bromine, bromine. Notice on this carbon and adjacent next door, we have in the ring two halogens. And what's bromine? X2. And what do you start with? A double bond. So the two carbons with the halogen are the two carbons in double bond. And therefore, we start with a ring with a methyl group, or end up, you better start with one. What are the two carbons with the halogen? These two, which are these two. And those two will be the ones in a double bond, which we show like that. If you react this with bromine, you will get this compound. And that's how you do synthesis. Now, they're more challenging. And that's why I'm only going to have one on test one. I think tests 2 and 3, I have 2 or 3 of them, and a couple on the final. Not too many. I don't know if I put one test 4. But I wanted to cover that because I forgot to do that at Dr. White. Oh, before I do that, any questions on that stuff? Remember, if you do, you can also come to my office hour tomorrow from 6 to 7. All right. Now, yesterday, I talked about this reaction, and this is a halogenation. This will be on test number 1. I'll finish this all today. And oh, by the way, tomorrow I will go through the aromatic problem set. So yesterday I showed you this reaction, and there are only 2 possibilities. And I did both. One I did as my example, and then you did yours. Now let's look at this, and I'll do this. And we have a benzene ring. Remember, 3 double bonds in a ring, benzene, in this case, and we're reacting with halogen gas and ferric trihalide. And here X is chlorine or bromine. And you replace one of the hydrogens with the halogen. Well, here it's chlorine, so I'll have my benzene ring. Don't forget to put the double bonds or circle in there. If not, cyclohexane. I take off points like all of them. And here, that would have a chlorine. Now, you also make HX, but that's an organic. You don't have to do it. Now, what if there's something on the ring already? I'll call Z, and I react it with something. Well, now you've got a whole different ball game, because where it goes makes a difference. When there's nothing on the ring, all the carbons are the same. And Z is called a director. How many of you have ever gone to, say, a concert or a flea market where they take a field and make it into a parking lot? And they've got those people who I don't like and they don't like me, who say, no, don't park there, go to the end of this aisle. We're filling it up this way. They're directing you where to go. Well, it turns out the group on the benzene ring direction where, in this case, the reaction I showed you, the halogen would go. Now, that's something most of you never will use the rest of your life. I'd rather spend time on proteins, carbohydrates, fats, and oils than I'm teaching you about directors. So I won't. But I will cover it in the lab, but anything I do in the lab will never be on test or the final. So you will get an understanding of it, but it won't be on test, which means the reactions I'm showing you now, there are only two I can show you, where X is chlorine and bromine. So we've done that. Let's go to the next reaction. And that's called nitration. If you take a benzene ring and react it with nitric acid, that's this, and sulfuric acid, you put a nitro group on a benzene ring. Now, I'm going to show you something that you don't need to memorize, but in case you were curious. Sulfuric acid, I'll show as H+. It's a general way. This is another way of writing nitric acid. And the electrons here on oxygen attract, the H+. This will never be on a test. And now the proton goes on that oxygen. The whole thing has a positive charge. Now, if you look right here, what's something molecule with two hydrogens and one oxygen? Two hydrogens, one oxygen, H2O, water. And whenever you form a stable molecule inside of another one, it says, I'm out of here. So you lose water and form the nitronium ion. And this is what attacks the benzene ring. It's an electrophile. Now, because I'm not teaching you directors, this is the only reaction I can put on a test. Now, remember, the nitro group is NO2. Common mistake, students put NO3. No, it's NO2. So this is the only reaction I can put on the test. So learn it. Now, same thing here. This is called sulfonation. And if you take sulfur trioxide and sulfuric acid, you'll put a sulfonic acid group. And this is the only reaction I can give you. Now, the previous halogenation, nitration, and sulfonation, I will never use as a synthesis problem. I'll say that again. Halogenation of aromatic compounds, nitration of aromatic compounds, these two right here, and sulfonation, I will never put on a test as a synthesis problem. Give the starting material. Now here, this reacts similar like I showed you. Don't forget the hydrogen there. People just put SO3 and it's wrong. And that's the sulfonic acid group, which I just mentioned the name, but you don't have to remember it. All right, now the last reaction for this chapter. There's some more stuff I'm going to go over, but it won't be on the test, but I thought I'd go over it. And that is called Friedel-Crafts Alkylation. For many eons, it's not done as much now. If you came up with an amazing reaction that was just something really earth-shattering, it was named after you. In this case, two chemists, Friedels and Crafts, worked together to come up with a reaction. Now, what's the reaction? The reaction is to take benzene, react it with an alkyl halide. R means something with carbons in it. X can be chlorine or bromine. You need a catalyst, aluminum trihalide, and you form something special, a carbon-carbon single bond between the benzene ring and the R group carbons. You also make HX, but that's inorganic, and I don't have to learn about that because organic chemists are biased against stuff inorganic, and I won't ask that on test. In all of organic chemistry, there's only a small handful of reactions where you can make a carbon-carbon single bond. Don't forget to put circular lines inside, otherwise that's cyclohexane, which would be wrong. Now, the bond from this carbon goes to the bond in R, the carbon in R, that has the halogen attached to it. The bond from the benzene ring to the carbon in R is to the same carbon that had the halogen on there. All right, let's do an example. And if you look on the screen right now, you see a benzene ring, carbon, 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 halogen, and we call that Rx. R is like in math, X and Y, that. So this is right here, my R group. And I have a halogen I can call X, and right here, I have aluminum trihalide. And remember, X can be chlorine or bromine. And you form that something special carbon-carbon single bond. So what carbon is the halogen on? The end one of my R group. So I'm going to have my benzene ring. Don't forget the bonds are circle. Then which carbon has the halogen, the end one? And that's how you do it. Oh, hold on one second. And that's how you do it. Again, the bond from the benzene ring to the R group goes to the carbon with the halogen. Do you break carbon-carbon single bonds? No. So I have 3 in the R group. There's 3 on the benzene ring. It's your turn. What would be the product or product for the following reaction? 3 points each. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's do this. What's different? Ooh, a benzene ring right here. And what do we have here? Carbon, carbon, oh, a halogen carbon. And how do we show that? Rx. R can be anything with carbons. X can be, for my class, chlorine or keep on forgetting, don't use cursive. This. And in this case, it is bromine. And what happens? You form a carbon-carbon single bond to the R group. And the carbon with the halogen is the carbon in R that this bond is bonded to. So what do we have here? Our benzene ring. Don't forget the lines or circles, or I take the 0 points. What's my R group? 3 carbons, isopropyl. And the center carbon has the halogen. And that's why it's bonded to the benzene ring. And that's how you do it. And let's move on. Now I can do a synthesis for this. Oh, let's try one. Now here, instead of putting it above, what two things with aluminum trichloride do you have to react to make this molecule? And that's the fun part of organic chemistry synthesis. Your turn. That should help you out. All right, I think everybody's done. Let's move ahead. Now, how do you find out what two things you react with aluminum trichloride to make this molecule? Well, what's different? Well, they've got a benzene ring. That's different. And notice here I have carbons and hydrogens. I'll call that R. And this right here is aluminum trihalide, where X can be chlorine or bromine. In this case, it's chlorine. So what do we start with? A benzene ring and an alkyl halide. Oops. So one of these question marks is a benzene ring. Don't forget to put the lines or a circle inside, which are double bonds. Now, what's our? Well, here, 2 carbons. Now, this one, the carbon bonded to the benzene ring, is the carbon with the halogen, which in this case is chlorine. And that's how you do synthesis. This reacting with this will make that compound. Now, for all the general reactions, other than the ones I said I'm not going to do, only one of those I'll use to do one problem on test 1. And with that, I'm going to say, let's take a 5-minute break, come back. Ooh, I went over. Ooh, sorry. 2:56, and I'll see you in 5 minutes. I'll go check my nail and stretch. Let's try it again. Let's get going. If you came in late, don't forget, I posted in D2L and you should get an email this Thursday after class. I'll send out the password, an email with the password for test number 1 PDF file that you can download from Blackboard, wrong school, D2L. Sorry about that. This morning I said, oh, you can find it in D2L. And they're looking at me like, what? I said, oh, wrong school. Anyways, here, ECC, you can download it from D2L. You'll have until Friday, 11 a.m. Now, I mentioned this Thursday, but I shall promise that by 1 p.m. Sunday, if not earlier, and I expect earlier, sometime Saturday, so I got some stuff I got to take care of on Friday, personal stuff. I will have your test number 1 score in D2L, and I will email to each of you an individual email that will show how many points you got for each answer. On Monday, I will go through the whole test with all the answers, and you can check, see if I made a mistake. And if I did, you should never be penalized for a mistake I make. But however, I shall tell you, when I go through that on Monday, the answers for test number 1, I'll cut that out. How do you like that? Am I good or not? Not. But anyways, I'll cut that out of the video. If you can't make it to class, then come to my office hour, arrange the time, and I'll go through that with you. All right, let's continue on. Now, the next couple of slides, I'm going to turn the switch. Will this be on a test or a final to the off position? But it's something I'd like to talk about, and I think you'd like to hear about. Now, there's a whole group of compounds called polycyclic aromatic hydrocarbons. Now, you know, cyclic means ring, aromatic has 2n plus 2 pi electrons, hydrocarbons only a carbon-hydrogen bonds, poly means many. And we'll learn later on, I'll use that term in polymers, many. There was a very nice woman, unfortunately, she passed away about 1.5 years ago. I think it was 1.5 years, a little over 1 year ago, who was for many, many years the Dean of English at Elgin Community College. And her name was Polly Minash. And the first time I met her years and years ago, through other friends of hers that I knew, I said, oh, Polly, do you know your name means many? And she gave me that look like, you know how many times I've heard that? She didn't say it, but she gave me that look, and I apologize. Great lady. Sorry she's gone. But anyways, what are polycyclic aromatic hydrocarbons? Those are aromatic rings, hydrocarbons, with more than one ring. You can have rings fused together that share common carbons. This is not going to be on the test. Remember, click, it's in the off position. But the simplest one is this compound. It has the common name naphthalene, and it's the main ingredient, the only ingredient in mothballs. And if you ever smelled mothballs, you're smelling naphthalene because that's all they are. And when I was a kid, my parents had a closet, cedar closet that's supposed to keep moths away. Moths like to eat wool. And they had a lot of mothballs in there. You could smell it. You opened the door to that closet. Oh, mothballs. All right, now I'd like to talk about graphite. Now, graphite comes from, is made of large sheets of polycyclic aromatic compounds stacked on top of each other. And let's go to the internet. Here's a piece of graphite. It looks like coal, but it's not. And if we look here, it's got sheets of cyclohexane rings, but they don't show it. It's really not cyclohexane. Each one is aromatic. That doesn't show a good job of it. They used to have a better images here, and they moved or changed it, which I'm sorry. That doesn't help. I wonder why they took it. They don't have it. Here's an example. All right, everybody see that on your screen now? And this keeps on going. It looks like chicken wire, except you've got double bonds throughout here that make this whole thing as aromatic. Now, if you think of sheets of graphite, it's used in lead pencils. By the way, since the Roman times, like 2,000 years ago or more, they don't use lead in lead pencils. When you write on a piece of paper with a pencil, what I'm doing when I did that, I'm laying sheets of graphite on there. Now, the individual sheets, and it's more than one, so you can see it, is called graphene. Now, it turned out for many, many years, people, chemists said, take a piece of graphite, you can't take one sheet of graphene off. Sort of like doing this. Assume this is graphite, and I would took one sheet off. This would just be one flat sheet of graphite, graphene. Well, it turned out about 10, 12 years ago, two very sharp scientists said, oh, let's use the crystallographer's technique, take some graphite, put some Scotch tape, pull it off, dissolve the Scotch tape into solution, and you'll have floating in there graphene. And they did that. And they won the Nobel Prize in chemistry, and rightly so. Now, graphene has amazing, graphene has amazing properties. The single sheet is strong, like steel, but it's light. And think about the possibilities if you could make stuff from that. And we, the United States and many other countries in the world, have been pumping billions of dollars into research like that. Now, same thing, graphite, which are the sheets of paper, but the sheets of cyclohexane rings that are aromatic, like benzene rings connect together. Back in 1995, both in Japan and in a college in Texas, organic chemists found they could take and treat the graphite, the big dark lump, with acid and other things, and take the graphene and make tubes out of it. And this has been, these tubes are again super strong like steel, but weigh almost nothing. And again, we've been pumping billions of dollars into research like that. And some of it's borne fruit, but I wanted to tell you about that. And those tubes are called nano tubes. They're a billionth of a meter, very tiny. Problem is we can't make large tons of it yet, bulk, but when we do, it will revolutionize everything. If you think about a car that's made of nanotubes or graphene, that the walls of the car, your doors and everything, are as strong as steel, but weigh like pieces of plastic. That will save on gas mileage. Same thing if you make planes out of that. So I just wanted to tell you that. All right. I've finished all the material for test number 1, which will be on Thursday when you can download the password and then have it up by Friday morning. But we've got a lot more to do this week, and let's move on. It's time for a new chapter, new functional group. This will not be on test number 1, but will be on test number 2. 1, 2. Oh, sorry. All right, let's get going. Well, first of all, I better open up the file. And don't forget, tomorrow I will do 2 important things for help you on test number 1, which is Thursday after class. And the first thing is tomorrow I will give my famous review for test number 1. Don't forget it's in the lecture section of D2L, but you got to click on at the bottom of the lecture where it says load more button, and then you'll see it. All right. It's new functional group time. Oh, am I excited? That excited. New functional group time. So what's this new functional group? Well, let's take a look. And the new functional group are alcohols. There's an alcohol. Now, an alcohol, the general formula is something with carbons that has a hydroxyl group, OH, on it. So anything with a carbon with the OH group is an alcohol. And we'll talk about all types of alcohols, not just the one you're familiar with. Now, let's go through, and I better start the next couple of chapters. I will be doing the same thing in general. I'll introduce you to the new functional group. Say hello to the alcohol. Oh, that was awful. And then we'll go through nomenclature. How do you name the structure? How do you take the name and draw the compound? Then if they're common names, I'll talk to you about it. There's special properties, I'll go over it. Then how do you make it? And the most important fun part is, how do you react it? And we'll do that now with alcohols. Now, the alcohol, for nomenclature, hydroxyl group in an alcohol is indicated. How do you know you have an alcohol? You find the longest chain that has the carbon with the OH on it, name it as an alkane. Then, since it's got a hydroxyl group, an alcohol, you drop the E and add OL. You drop the E and O, add OL. And then you use a number like a double bond to denote which carbon the hydroxyl group is on. And that carbon always gets the lowest number. If it's in a ring, it's always number 1. And the rest of the IUPAC rules are the same. So let's do some work. All right, let's take a look at that molecule. Everybody see it on your screen? Thank you. All right, now, as I've been saying, and now it gets even more important, when you look at a molecule, look for what's different. what's not a carbon-carbon single bond, or more importantly, what's not carbon or hydrogen. And oh, look, an oxygen with a hydrogen on a carbon. It's an alcohol. So how do you name it? Find the longest chain that has the hydroxyl group on the carbon. And that carbon should be in that longest chain. And here, that's 4. 4 is butane, but it's an alcohol, and we use OL ending, butanol. This is OL. Now, next, when it's in on an acyclic compound, not in a ring, you have to say which carbon is it on. It always gets the lowest number. If we start here, it's on carbon 1. We start here, 1, 2, 3, 4. I think you all agree 1 is less than 4. And that's 1 butanol. And that's how you do it. Let's go through it again. Now, what do? You find what's different. In this case, hydroxyl group on carbon, the oxygen gives it away. That's an alcohol. You find the longest chain with the carbon with the hydroxyl group. You name it as an alkane, 4 carbons, butane. You drop the E and put OL, butanol. And then which carbon has the hydroxyl group? In this case, carbon 1. And now it's your turn. And the question is, what's the IUPAC name for the following molecule? Your turn. Remember, find the longest chain with the hydroxyl group on it, name it as an alkane, drop the E, add OL, and then figure out what carbon the OH group is on, and always has the lowest number. All right, let's do this. So you look for what's different, what's not carbon, what's not hydrogen. Ooh, an oxygen with a hydrogen. What is that on carbon? It's an alcohol. Oh, excuse me. Now, how many carbons longest chain? 1, 2, 3, 4, 5, 6. What's 6? Hexane. Drop the E in hexane because it's an alcohol. We use OL, hexanol. Now, what carbon is it on? Well, if I start from here, it's on carbon 2. If I start from this side, 1, 2, 3, 4, 5, which is smaller, 2 or 5 and times up, and this is 2-hexanol. Now, if you have alkyl groups, you do it the same way we've already done. So I'll have you try one. And there's one for you to try. Give the IUPAC name for the following. All right, I think everybody's done. Let's do this. What do? You look at a molecule, look for what's different, what's not. Carbon, hydrogen. Ooh, an oxygen with a hydrogen on carbons. Remember, R is anything with carbon or hydrogens. It's an alcohol. Now, here, what's the longest chain? 1, 2, 3, 4. I'm back. Since yesterday's storm, I don't know what it did to it's never happened before. Yesterday and just now today, I lost power for a fraction of a second, which wasn't long enough for my UPS to kick in, and my computer shut down. So if you lose me, I'll be back. Everybody see me? Give me a thumbs up if you can see me and hear me. Thank you, Jimmy. All right, let's get back. I got to open up some files. Hold on. All right. I believe this was the example I had on there. Give me a thumbs up if somebody remembers that's what I had. Well, let's go through this and I'll do another one. All right. How do you do the name of this? You find the longest chain with the hydroxyl group. 1, 2, 3, 4, 5, 6. I think I did this. And that would be hexane. Drop the E, add OL, and it's on carbon 2,2-hexanol. All right. Let's do one where you have, I think this is what I had on there. Now that I remember. And the longest chain with the carbon with the hydroxyl group Y, that's an alcohol. And we have 1, 2, 3, 4 carbons. And that would be butane, but it's an alcohol. So I drop the E on butane, add OL. Yeah. And it's butanol. But what carbon is it on? Carbon 1. So it's 1-butanol. Am I done? No, it's your old friend, the methyl group. And what carbon is it on? Carbon 3. So this is 3-methyl 1-butanol. Now, for rings, the carbon that the hydroxyl group is on is always number 1 when there are no other functional groups, which will be true in this class, and you don't need a number. So how many carbons in this ring? 1, 2, 3, 4, 5. That's pentane. It's a ring, cyclopentane. It's an alcohol. So it's cyclopentanol. And because that's the only thing on the ring, I'm done. You don't put 1 there, because when there's only 1 hydroxyl group alcohol in a ring, no other functional groups, that carbon will always be number 1. Now, you name the rest of the functional groups just like you always did, number them. But the carbon with the hydroxyl group is always going to be 1. And your turn, what would be the IUPAC name for that molecule? By the way, everybody, don't forget to make an offering to the gods of electricity for Dr. White. I wonder if something happened because of all the electricity from the air conditioners running now. Oops. What's the temperature while you're doing that? I'm going to check something real quick. Wow, where I live here in Schaumburg, 96, but it feels like 104. Yikes. Remember, this material will be on test 2, not test 1. Test 2 will have the alcohols, not test 1. And don't forget, it's now available, but you got to click on the load more button at the bottom of the lecture folder of T2L to see test number 1 review. I'll go over it tomorrow, but you might want to do it tonight. See what reactions you should know. All right, let's do this. What do we have that's different? That's not carbon or hydrogen. Ooh, oxygen with a hydrogen on a carbon. And that's a alcohol. And now, ooh, it's on a ring. How many carbons? 1, 2, 3, 4, 5, 6. That's cyclohexane. Drop the E, add OL, cyclohexanol. This carbon is always going to be 1 when that's the only hydroxyl group or functional group in a ring. And you count in such a way that the other alkyl groups, and what is this, an ethyl group, at the lowest number, and that would be 2, 3. So that's 3-ethyl cyclohexanol. Again, ring with hydroxyl groups. And how many carbons? 6. Each bend line is a carbon, end line is a carbon. All right, and therefore 6 cyclohexane. Don't forget the cyclo. On test 2, when you do this, drop the E, add OL because it's the alcohol, and you've got your molecule. All right, now on test number 2, like test number 1, there are going to be 2 types of nomenclature question. 1, here's the molecule, give the IUPAC name. The other is, here's the name and draw the structure. Oh, one thing I should mention, everybody, a common name that became the IUPAC name that you need to know, and this I pronounce phenol. A lot of people call it, I don't want to say I will. Phenol, nah, that's wrong. Actually, I worked for a company that bought a lot of phenol. We went through a couple million pounds a week. Yes, a week. And I had a running argument with the chemist there. How do you pronounce it? But anyways, benzene ring with the hydroxyl group is called phenol. No, it's phenol. And just like toluene, if you have something on there, it would be substituted. And if it's 2, like this, what's the name of this molecule? Well, I got a benzene ring with a hydroxyl group, so the root name is phenol. Oh, I've got an ethyl group, and this is 1, 2, 3. Remember, for aromatic rings, disubstituted, and the hydroxyl group, just like in toluene, counts as a substituent on the ring, and therefore this is used ortho, which is 1, 2 disubstitute, meta, which is 1, 3 disubstitute, and finally para, which is 1, 4 disubstitute. So this has an ethyl group, so it's ethyl phenol, and it's 1, 3, making it meta ethyl phenol. Now let's go. All right, so the question is 3 points each. Draw the structure for, in this case, A, 2-methyl pentanol. How do you do that? You start from the right and move left. OL ending tells you alcohol. Pentane, if that OL were an E, would be 5 carbons. And now here's something important. When I took organic chemistry, my instructor, and he did something I'm sure he learned from his instructor. We always, for oxygen functional groups, put them on the right. You can put them on the left, but most organic chemists. So, oops, I made a mistake. That should be 1 pentanol, 2-methyl 1 pentanol. So I'm going to start here, 1. The OH from the alcohol is there. This is carbon 2. I'll have a methyl group, and I know how to put in hydrogens because there are 4 bonds to carbon. Now, you could have just as easily, and I got to force myself because it looks unnatural to me, but this is totally correct. We have 5 carbons. The hydroxyl group is on carbon 1 and carbon 2. We have a methyl group. And there it is. Are they the same? Yes. Left hand, left hand. Now, in my class, I'm going to draw it this way. You can feel free to put that on a test that way. They're both identical. You just rotate it 180 degrees. But I just thought I'd warn you about that. All right, your turn. And why don't you draw the structure for 4-methyl-2-octanol? I relaunched the poll. I started it too early. Sorry. All right, let's do this one. How do you determine what to draw? Well, you start from the right, move left. OL ending. Alcohol. If this were an E, octane is 8 carbons. Now, where's the hydroxyl group? On carbon 2. I'm going to number this way. You could do the other way too. And notice, oh, as we keep on going, it's your old friend, the methyl group on carbon 4. And now I know there are 4 bonds to carbon, and I'll put in the hydrogens. And there's the molecule. 4-methyl, 2-octanol. Let's do one more. And here it is. Ah, my brain just short-circuited. And here's one more for you to do. In fact, stop. Ooh, that was powerful. It's about time to take a break. Let's take the break instead of going into it. We'll come back and do this. We'll come back at 3:50 and give you a whole 30 seconds more than just 5 minutes on the break. And we'll continue on. And we'll also do the alkenes, the alkanes lab. It also has some double bonds in it too. See you in 5. Time to get going. All right, let's go back. And the question is, draw the structure for the following molecule. And it's your turn. 3-isopropyl cyclohexanol. Please draw it. All right, I think everybody's done. So let's do this. How do you do it? You start from the right and move left. OL ending, alcohol, hydroxyl group on a carbon. If this were an E, it'd be cyclohexane. But it's cyclohexanol, and most of you will put the hydrox group there. Now, as we continue going, we have an isopropyl group, 3 carbons, center carbon attached to the ring, it's on carbon 3. Well, it's going to be 1, 2, this is 3. And there you go, 3-isopropyl cyclohexanol. Now, there's one small little alcohol you're probably familiar with, and that's called ethanol. OL ending, alcohol, and I'll do this one. And if that were E-ethane, 2 carbons, and one of those carbons has a hydroxyl group. And you might want to say, Dr. White, how come there's no number? Well, you have 2 carbons. The carbon the hydroxyl group is going to be on has to always be 1. Whether you draw it this way or that way. Since there's no possibility of 2-ethanol. Everybody knows that. Well, we're not going to even have to put a number. Now, this small little molecule has amazing physiological effects on the human body. This is what we call alcohol. This is the molecule in beer, wine, and also hard spirits, like the good stuff, vodka. And if you consume too much of it, which in no way I am professing you should ever, you will get inebriated, which is a fancy word for saying drunk, which you shouldn't do either. But I thought I'd point it out. Now, it turns out alcohols have been around for eons. The Egyptians, the Romans, they all had alcohols. And because it's been around so long, way before IUPAC, they're common names that are still widely used today. In fact, more than the IUPAC name. How do you do a common name? The common name is derived, remember, alcohol. You name the chain the hydroxyl group is on, this R group, as an alkyl group, and then you add the name alcohol at the end. And I got to get to work. It says Seaboard for all this stuff. Well, I better get to work. Got a lot of work to do. And this is something, this is one of the few common names I'd like you to know. When it comes to common names, I'll never ask you, here's a structure, what is name, but I will ask on test. Remember, this is for test number 2 stuff. Here's the name, draw the structure. Now, we just went through this, and this is ethanol. And the IUPAC name, what's this R group? Ethyl. And then add the word alcohol. Now, where do you see the name ethyl alcohol? Well, you go look at a bottle of wine. They don't call it ethanol. They call it ethyl alcohol. But if you go to your local gas station and drive in there, you'll see a sign by the gas pumps, each set of gas pumps. This gasoline contains up to 10% ethanol. So next time you're in a gas station, you can point that out to a friend, neighbor, or loved one. Say, you know, that's the IUPAC name for an alcohol with 2 carbons. No, you don't have to do that. All right, let's look at this one. There's 1, 2, 3 carbons. And the hydroxyl group is on carbon 2. So that would be 2 propanol, which nobody calls it this. Notice this right here is an isopropyl group. And the R group is isopropyl. Then you add the name alcohol. And the common name for that molecule is isopropyl alcohol. Now, if you take anywhere from 70 to 90% isopropyl alcohol. And if you work in the chemical industry, we call it IPA. You take anywhere from, if you have 70% isopropyl alcohol, and you add 30% water, it adds up to 100. Or if you have 90% isopropyl alcohol and 10% water, it adds up to 100. You have a product. And what do we call that product? Rubbing alcohol. Now, for many, many years, you could only buy the 70-30. And about 10 years ago, they started selling also the 90-10. And I keep both in the house. Rubbing alcohol is an amazing disinfectant, and it works on COVID-19. Quick story, do I have that? I do. When I was a little boy, am I in focus? Hold on. I don't know why it's not focusing, or my eyes not focused. Nope, it's me. I wonder if that power outage did something. Let's try something. That's better. Aren't you glad you have a power user? But anyways, when I was a boy, and actually through high school, that's a long time ago, even college, you went to a doctor's office. The first thing they did when you got in the examining room was shove a thermometer under your tongue. Those were the old glass mercury ones. And it tasted awful. Why? To keep from getting people sick from someone else who might be sick, they would take the thermometer, and it was a V-shaped container, glass, that was full of isopropyl alcohol. And they stick the thermometer in there after they used it. Before they stuck it in your mouth, they take some cotton and wipe it off, but they didn't get all the isopropyl alcohol, and it didn't taste good at all. But anyways, that killed all the germs on there or whatever, so you wouldn't get sick. And the last common name I'd like you to know, if we look over here, but all I've done is rotate this 90 degrees to make this. And here we have 1, 2, 3 carbons. That's propane. It's an alcohol, propanol. This is carbon 2 propanol. And if this is the longest chain, what do I have? Oh, it's your old friend, the methyl group. Nobody ever calls that molecule 2-methyl-2-propanol, which is the correct IUPAC. No, we use the common name. If you look over here, what's 3 carbons on a center carbon attached to something else? A T or tert-butyl group. And add the name alcohol, and all organic chemists call it T-butyl alcohol. So you should know these. On a test, if I ask, draw the structure of ethyl alcohol, you should know that. Isopropyl alcohol, you should know that. T-butyl alcohol. And the next time you're out and about, or if you have in your house, pick up a bottle, if you have it, of that hand sanitizer. And what's in there? It's about 65% ethanol. Ethanol also does a good job of killing bacteria and viruses. And when the pandemic hit, you know, it was the first thing Dr. White did. I went to my local liquor store and got what they call Everclear. Got one of the last bottles, in fact. Not that I'm telling you. And Everclear is 190 proof. That's pretty strong stuff. But this is one of the best things to have in your house for if you need a disinfectant. And what the proof means is if you divide that by 2, it's 95% alcohol. Why isn't it 100? When you need to get all the water out by distillation, it's called steam distillation, or not steam, azeotrope distillation. You're going to have some benzene left in there, toluene, which you don't want to ever have that drinking. So that's why Everclear is 190 proof. And you don't drink this stuff straight, you can't, you get sick real quick. But that's what I have in my house. I've got a bottle for emergency because of the pandemic. And also, I do the same thing. I bought up some 90. It's hard to find, but I was able to find some. And then recently, it's easy to find the 90% isopropyl alcohol, because that's also good and disinfectant to have in the house for emergencies. All right, if I look at the clock, and I'm looking at the clock, I think it's time for today's lab. Yay. Remember, the stuff on alcohols is for test 2, not the test number 1 coming up this Thursday after class. And don't forget, tomorrow, I will do my world famous review for test number 1. It's also in D2L, but don't forget to push the button with your mouse, load more to find it. And also tomorrow, I will go through the aromatic problem set. That's not what I wanted to do, sorry. All right, thumbs up, people. Everybody see alkanes and alkenes problem set on your screen. Oh, thank you, Jimmy. All right, today's lab deals with alkanes and alkenes. And if we were in the lab, I would remind you, hydrocarbons and saturated or unsaturated are very flammable. And we never in an organic lab light any matches or Bunsen burners or lighters. You get a fire. And I'll tell you, we have disposal bottles. We never dump anything like this down the sink. All right, now, since we can't do this, but I'll talk about it. I have the data for you. One of the things these labs were meant to do, and they do if we were face-to-face, and even now, you can get some idea, is to get a feel for handling certain hydrocarbons. Now, the first part deals with odors. What does it smell like? And in this experiment, I believe all but one are liquids. Dr. Daly, who's the lab manager years ago, I used to have students rip up paper towels. When he became manager, he said, "Do you want me to cut up some for you?" And I said, "That'd be great." And the students loved it. We have 2-inch by 2-inch pieces of paper towel that to smell it, you never put your nose over a bottle of a chemical. Take a piece of paper, put a few drops, and go like this and smell it. And you put down what it smells like. And here I have a number of compounds to smell, and I've given you what it smells like. Now, if you notice right here, it says draw the structures underneath the name. And when you do this, underneath these names, draw what hexane is, octane. Now, I don't have a number here because when we do the lab, it matters what Dr. Daly, does he have 1 octane, 2 octane, maybe sometimes even 3 octane. For this one, why don't you put 1 octane? Now, limonene, you can go to Google, same thing I talked about naphthalene, but you can look it up on the internet. And this, I gave you the observations. This is what students have told me over the years. All right, the next one deals with a very interesting reaction that helps you identify, does the molecule have a double bond or not? And how does that do that? Now here I have a general reaction, but let me show it on the whiteboard. You have a double bond and you react it with the halogen like chlorine, fluorine, chlorine, bromine, or iodine. You break the pi bond and each carbon gets a halogen. And this happens really quick. You don't need a catalyst. Well, the reaction to help identify, and this was before organic chemists had the electronic equipment we now have, the spectroscopic equipment to do this, but back then they didn't, back in the late 1800s through 1940s, 1950s. And if you wanted to find out, does this molecule have a double bond? This is the test you did. You reacted it with a bromine solution. Now, this is a reddish brown. My sisters always yell at me, you don't know your colors, but you get the message. Now, this is a clear or light yellow color. All or most organic compounds that are liquids are. And if you have a double bond, this reacts. And this dibromo, di-2-bromo compound will also be clear or light yellow. So if you have double bond, you add the reddish brown solution to an unknown. If it stays clear, you have a double bond. If it goes red, the bromine didn't react, and you don't have a double bond. I've got the hiccups. I know I got that. I guess I'm allergic to bromine. No, by the way, bromine is very dangerous. But in the lab, I do this as a demonstration. And let's look at the following YouTube. It's a short one, so let's take a look. All right, thumbs up, people. Do you see on the screen the 2 test tubes? Thank you. And let me move this out of the way. Now, let's start this again. On the right is an alkane, no double bond. On the left, on the right is an alkene, double bond. Now they're adding the bromine solution. And see how it's turning a reddish brown? That's because nothing is reacting with the bromine. I actually do this for you because bromine is very dangerous to handle. Now here, double bond, see how quickly that's reacting? And it's staying clear. That's because the bromine is reacting with double bond, making the dibromo compound, which is clear. And that's what I wanted to show you. Now in this reaction, for this part, I do this. A reason why years ago at the other school, we did this, and somehow one student got bromine on the back of the neck of another. I figured out finally how it happened by accident, but we had to send this, first I had to wash it off real quick, send the students, at that time we had a nurse on campus, to check to make sure he wasn't burned badly or at all. Luckily I got it off quick enough by the bromine. But anyways, you're going to be reacting with cyclohexane, 1-hexene, and again, I don't know always, let's make it 1-octene, limonene, and to make it interesting, unknown A and unknown B. And if you were in the lab, you'd watch me, and the data you would observe that I'd show you is when you add it to the cyclohexane, it's reddish brown in the test tube. The 1-hexene stays clear, the 1-octene stays clear, the limonene stays clear, they all have double bonds, and then unknown A stays clear, unknown B stays reddish brown or goes reddish brown. And what you have to do is there's some questions concerning your knowledge of what I just said and unknown A and B. Now, let's move on. Now, there's another way of finding double bonds. And this is a reaction I didn't talk about in the lecture. And remember, anything we talk about in the lab will never be on a test. But this is an interesting reaction. And let me show you it on my whiteboard. And if you have a double bond and you react it with potassium permanganate, KMNO4, and we have this in this acidic solution, helps it go quicker. What happens is this breaks the pi bond, oxidizes it, and you get this diol, di2OL alcohol. Now, how does this work to show a double bond? Potassium permanganate solution is purple. That one I know for sure. Now, when it oxidizes, and that's what this reaction is called, the double bond, the potassium permanganate is reduced, and you get manganese dioxide. And the best way, if you ever make this, and you would have done this in the lab, this looks like a muddy brown color. Think of taking dirt and putting some water in it and looking at it in a container. That's what a magnesium dioxide looks like in a test tube. And it coats the walls this sort of muddy brown color. So if you have a double bond in a molecule and you add purple potassium permanganate solution and you see a muddy brown color, you've got a double bond. If you see it go purple, the potassium permanganate didn't react and you don't have a double bond. And what you do is some test tubes put in what you're testing, about 5 drops of the alkane or alkene, put about 10 drops of the dilute potassium permanganate, mix it, wait a couple minutes, and then look Is it purple or muddy brown? And let's look at this YouTube video.
My job is to make college easier because
unfortunately, there's a commercial. Now I can skip the ad.
Shaking a liquid alkene with brown-yellow bromine water results in the decolorizing of the solution due to the formation of a colorless dibromo compound.
That you've already seen.
Gaseous alkenes, such as ethene, can be detected by passing them through bromine water with a similar result.
Same thing, double bond reacts to bromine and it goes clear. We don't do that in the lab.
An alkaline solution of potassium manganate 7 oxidizes alkenes to the corresponding diols. Dark purple manganate 7 ions are reduced to insoluble brown manganese 4 oxide, which produces a turbid brownish suspension.
I don't know why this garbage, I can't move.
Analysis of its combustion products is a common method for determining the empirical formula of a compound. Analysis of its combustion products is a common method for determining the empirical formula of a compound. Most organic compounds will burn in air when ignited.
I don't know. Nope, that's not the one I had. Let's see if I can get back to that one again.
An alkaline solution of potassium manganate 7 oxidizes alkenes to the corresponding diols. Dark purple manganate 7 ions are reduced to insoluble brown manganese.
I'm sorry, I don't know
oxide,
why that's coming
which
back.
produces a turbid brownish suspension.
But you see that particulate in there? I call it muddy brown. When you get that, that means you have a double bond. So put the different, some potassium permanganate KMnO4 solution in test tubes, add some of what you're testing, mix it and observe. And here you have cyclohexane, 1-hexene. This, let's assume Dr. Daly gave us 1-octene, limonene, and oh, look, it's unknown A and B. Now, if we look up above, the cyclohexane, no double bond, so the solution is purple. 1-hexene, 1-octene, and limonene have a double bond, muddy brown. And when you do it with unknown A, you get a muddy brown color. Unknown B, it's purple. And here, notice the questions I have. Please use your experimental results to justify your answers. Now in one, all I'm asking you to do is draw the structures. And then here are the other questions. And finally, number 4, please identify A and B, unknown A and B, not the full name, just is it an alkane or an alkene? And the hard part, not that hard, describe what data in your experimental results in the tables above in part 2 and 3 allow you to make that identification. And with that, I'm done. It's a lab day. We get out early on lab days. And I'll say, gang gesund. I'll see you tomorrow. Don't forget, tomorrow I will be doing the review for test number 1, and we'll also do the aromatic compounds problem set. And then when we finish all that, we'll go back to alcohols, which will be on test number 2. With that, gang gesund. Goodbye.